In this video, we're going to talk about line integrals, or sometimes called path integrals. Now, in this video, we're going to do two major things. First, we're going to introduce the idea of what is a line integral? What's the big idea? What problem are we trying to solve? And then secondly, we're going to work towards coming up with a formula that lets us compute line integrals. And then in later videos, we're going to see examples and other applications of line integrals. Again, links to those in the description. Now, before we jump into the math, before we see any graphics, here's one way to visualize the idea of a line integral. Imagine it snowed, and there's snow banks everywhere outside. At some spots the snow is higher, and at some spots the snow is less high. And you want to go and walk out into the snow, shoveling as you go. The question is, how much do you have to actually shovel when you go out and walk from your back door? Well, it depends on the path you take. So it certainly depends on how far you go. For example, if you go further, there's going to be more snow that you're having to shovel as you go away. But it also depends on where you go with the length that you decide to walk. For example, if you walk along through big snow drifts that are really deep, then you'd have to shovel a lot more snow. So what the line integral captures is this notion of an accumulation, in this case of snow, above a particular curve. Okay, so let's see a little bit more concretely what I mean with some mathematics formalism. Let's just begin in the simpler scenario we know well, a simple function f of x from one variable to another. And the important thing is, if I look down at the domain, well, the domain I can think of is just some line segment on the x-axis. This is kind of like a curve that's just constrained to be only the x-axis. And then the f of x tells me the height above that line segment. And then if I'm interested in figuring out, well, what is the area? Well, we know the answer from single variable calculus. Integration was the answer to the question, what is the area above some interval and underneath some function f of x? Okay, so now let's go up a dimension. Now my input is two-dimensional. It's the xy plane. And in the xy plane, I have not a line segment, but some other curve. In this case, it is a circle. I'm going to have a height above that, a third dimension in a moment, but right now I'm saying my inputs is going to be this xy plane, and in particular, this circle in the xy plane. I can talk about this a bit more generally by parameterizing a generic curve, which we call C. And the way I parameterize curves is I write it r of t is going to be an x component, g of t, in the I hat direction, and then a y component, h of t, in the j hat direction. And if I am parameterizing it like this, I need to specify some domain of my parameter t, so I say t is in some interval a up to b. In this specific example, my functions might be 2 cosine of t in the x and 2 sine of t in the y, and my interval might be 0 to 2 pi. But you can do this for any curve. The idea of parameterizing something means that you've got this single variable input t, but that what you get out of it is this two-dimensional thing, this r of t. And indeed, note that the r of t I've written here is two-dimensional. I don't yet have a third component to it. Okay, so now let me plot a new curve. Well, this curve has the same x and y components, but instead of having a z component being 0, it now has a z component being some arbitrary height. And I can call this height f of x and y. It's some function of x and y. Now, if I focus specifically on the x and y that are along this curve, I could substitute in that this is f of a g of t and of an h of t. That is, my third component is now just some other function of t. And by the way, a very natural way to represent parametric curves is as I did earlier with my animation. As time went on, more and more of the curve was drawn. This is a great way to represent a parametric curve. Now, it might be the case that the function f of xy is actually defined on many more points than just the curve C. For example, when I was figuring out this animation, I actually have my f of xy being some paraboloid. It's defined on many more points than just the curve. The only parts of the function I care about are those above this curve. And then my final step is just to shade everything in, so at any point along my curve C, I just draw up until I hit the blue to the height f of xy, and that's what I get. So the question is, what is the surface area of this resulting shape? What is that area? Now, at this point in our calculus development, we've seen a lot of times where we've tried to tackle a geometric problem like finding an area, for example, and we've used integration. And the big idea has always been to break it into small little pieces. That's the big idea of integration. Take some complex problem you can't solve, like what is the surface area of this thing? Break it into a much smaller thing you can solve and go from there. So for example, instead of this nice, clear, continuous, what if I break it up into a bunch of smaller rectangular chunks? This is an approximation for the original surface area I want to compute. Okay, let me break out on exactly how I got those. If I start with my pair of curves, my first step is to take the time interval. Remember, the t was your parameter here, and it ranged between a and b. Take that time interval and break it into n different components. And what you can see here is that in the graph, I just plotted a lot of points, and those just represent, as I'm trying and drawing those curves, what happens when my t is 1/n of the way, 2/n of the way, 3/n of the way, and so on. Okay, and then the next step is I'm going to draw line segments between all of these points. And notice I've done it twice. First down in the circle, I've taken my circle and approximated by a bunch of little line segments, and then likewise on the blue curve as well. And then the next thing I'm going to do is create a whole bunch of rectangles. This is just one of those sample rectangles, and these are just going to connect a bunch of these points. But the big idea of integration has always been that yes, you can do this, but then you just increase your n more and more. So for example, if I wanted to have more points, I've doubled the number of points, or double the number of points again, my rectangle gets smaller. And it was never quite right because there's always like a little bit of a gap at the top, like it never fit perfectly, but when you get more and more n, those gaps get smaller and smaller. That's the big idea. Okay, so let's return to the slightly larger one. In fact, I even want to zoom in on it. Now, this rectangle, I want to figure out what's its area, because I'm going to add up the area of all of these rectangles, so I want to know the area of one of them. Well, the height is just the function value at whatever particular point you're at. Indeed, I'm imagining that I'm at the kth point. Remember, I have n in total, so if I'm at some k in the middle there, then I'm going to figure out, well, what is the function at that kth value? So there's an xk and a yk. There's kind of a bit of a choice here. Notice the rectangle actually goes from the kth point to the k plus 1th point. So I could have chosen the height of the k plus 1th point as well, or I could have chosen halfway between those. There's some options. I've sort of chosen the left endpoint approximation. In the limit as n goes to infinity, it's not going to matter. Okay, so that's the height. And then, well, what about the base? The base now I call delta sk. S is the symbol for arc length. So basically I'm saying, well, I've got a little arc length down here on the bottom. I'm going to call that delta sk. We're going to investigate it more in a moment, but right now I'm just going to call it sk. And then, well, what's my rectangle? It's these two things, but just multiplied together. It's got the height, the f of xk, yk, and then it's got the width, the delta sk. And together, that is my delta ak, my little area, my kth area. Okay, so now we're ready to finally define what we mean by a line integral. So here it is. It's some fancy set of symbols. And notice, this is a new symbol that we have not seen before. This is not an integral from a up to b. It's an integral with a subscript of c. And that just means a line integral over a curve. That's how I interpret this. And then for the integrand, I've put my f of xy analogous to my normal heights that I put in my integrand. And then I wrote ds for my little infinitesimal increase in the arc length s. Okay, so this is a new symbol. How is it defined? Well, it says, let's look at that approximation and take the limit when I sum up all of those different things. That is the standard Riemann integral definition, but for this situation. It's a limit as n goes to infinity. You break it up into as many pieces as possible. And then you sum up all of those delta AKs, and that is my formal definition. Okay, so this is pretty good, as in I've come up with a definition that's analogous to any number of definitions earlier in calculus for computing areas and volumes of things. But as you'll recall, limits of sums are not easy to compute. So this might be the formal definition, but I also want to come up with a formula that lets me compute this limit of the sum easier without actually having to do a limit of a sum, because that is very, very tedious. I want a quick computation. So let's actually return just back a little bit in our definition, where we had the area of a rectangle, and we decided that its height was f of xk and yk, and that its base was the delta sk. I want to do better here. So let me focus on specifically the delta sk. Well, if I imagine what's happening in the base, this change in arc length, there's a change in the x, and there's a change in the y. And so the change in the arc length by Pythagoras is just going to be the same thing as, well, the square root of the sum of the squares, the change in the x squared, that is, plus the change in the y squared, that is, square root it. And so now I've managed to actually improve what my delta sk is. Okay, so now let's go back up. Same story we had before, delta ak, exactly what we just saw. I've got my height, my f, but now my delta sk is being replaced by this Pythagorean thing. Now I'm going to do a little bit of a trick on this delta sk business. In fact, it's the exact same trick that we did back in multivariable calculus. I'll make sure to link the video, when we were coming up with a formula for the arc length of a curve back in multivariable calculus. The trick was, I'm going to divide and multiply by the delta t. And so there's a delta t on the outside, and then because of the square root, there's delta t squareds on the bottom. I just multiplied by 1. And then when I take the limit as n goes to infinity here, a couple different things happen. First, the f of xk, yk just turns into the f of the x and the y at that specific point t, so g of t and h of t. So the f just changes from at a specific point to as a function of t. And then more importantly, if you look at the delta xk over delta t, as n goes to infinity, this turns into the derivative of the x component. The x component was called g, so it turns into g prime. And then likewise, delta yk over the delta t, that in the limit as n goes to infinity also turns into h prime. And so either way, I get this new formula in terms of the derivatives, this g prime squared and this h prime squared. Okay, so if I just focus on this, now that is what I'm going to integrate. And so I have a new formula for my line integral. The line integral, the integral with respect to some curve c of f of x, y ds, is now going to be just the integral from a to b. Hey, this is something I can do now. This is one of my old single variable integrals. This is an integral in terms of t. So I can compute that. Oh, anyways, I plug it in, f of g of t and h of t, and the square root of g prime squared plus h prime squared. So here's the point. If you know what your g of t is, your h of t is, and your f of t is, and you know the bounds of your parameterization, the a and the b, well, this is just an integral. You plug everything in and you can compute it. The way I think about this is all of that business with the square root of g prime squared plus h prime squared dt, all of that is just the expanded form of just the little arc length, the little ds. And so when I look at my picture, I think that I am trying to add up a whole bunch of little components. My components have the height, the f, and they have the width, the little ds. And that's what I think of this formula. So in fact, I don't go through the whole process of deriving this formula every time. When I just look at this formula, I think, okay, I'm trying to figure out the surface area. It's just heights times little ds's. And we previously analyzed little ds can be written with this big square root stuff. Okay, what are we going to do over the course of the next couple of videos? Well, first, I definitely owe you a concrete example of this. So in the next video, we're going to have actual functions listed and run through a process of computing a line integral in a specific example. But then secondly, I actually want to show you that there's many, many more applications of line integrals than the specific one we saw in this video of computing this surface area. Indeed, it turns out that the original curve C was two-dimensional in our example, but you could have those curves being three-dimensional or even higher. And indeed, the thing you might be caring about might not be a geometric property like a surface area. There can be all sorts of other properties that you might be interested in that a line integral allows you to compute.